All right. We're on the air here. John's late. Now everybody in the universe knows. Our first speaker today will be Carlos Broto, who is speaking on something I can't read because it's
so small. Yeah, okay, so. No, I cannot read it. So this is homotopy fixed points by finite P group actions on classifying space of fusion systems. It's a long title. So there is little I can add to these titles. This is joint work with my former student and colleague Alex Gonzalez. So this is actually a work by Broto and Gonzalez, means by BG. Well, so this is very appropriate for the talk. So we will fix throughout a fixed prime number. Fixed prime number, and we'll have some finite P group on pi. Finite P group. So the purpose of the talk is to explain and maybe give some idea of the proof of the following result that I will write and try to explain what is in the formula. So we have an action of pi and certain classifying space, whatever it is, and then we want to compute homotopy fixed points by the group pi. So pi is acting here, and I will assume that this is not empty. So in this case, we show that this is homotopy equivalent to a union of components, which is indexed by some non-abelian cohomology group, phi, with certain coefficients depending on this f. And so I take elements here, and then I will write another classifying space. Like this. So, so this is what the theorem I want to show. Well, if you change f by g and write p completion, then this is a known formula already, right? So this was known. Perhaps not written in the literature as far as I know, but it was known for finite groups. In the case the action is trivial, then this is also known, because this turns out to be trivial action. Then these homotopy fixed points become the space of maps from d pi to this other classifying space, and this turns out to be a union over the, here would be representations of phi in f, and this would be some centralizers of the image of pi by some representation. Right. And this was, and that was proved by Oliver Levy and myself. So this is a generalization of such a result. When we put here a group, this is well known, that's due to Dwyer and Zabrodsky, a group and P completion. And right, so what I would like to explain is what are the ingredients that we see in this formula. So what is this F and what is the classifying space of F? So what is a fusion system? What is the classifying space of a fusion system? Right?
When you said assume non-empty, was it? Do you have a criterion for
Not really. Not really. The point when you define the action on some model of the classifying space, then maybe you have a criterion. For instance, that the classifying space has a unique vertex, and this is what happens in the other side. So. Yeah, that's what happens if we put here a group and we take the action of pi on the group, then the trivial element of the group is fixed. Okay, so as what about fusion systems? So this goes back to the so-called Martino-Pridi conjecture. Which is now a theorem by Oliver.
Did you say Martino-Pridi?
Martino-Pridi, yeah. A theorem by Oliver. That says that the homotopy type of BGP completed, classifying the space of a finite group. And the group is control is determined by a key local structure of the group G. So to make this precise, what do we mean by key local structure of G? We fix choose and fix a Sylow subgroup. Sylow is subgroup of the group G, and then define the fusion system. The fusion system of the group G over the Sylow subgroup S, which is a category with objects with subgroups in S and with morphisms given by conjugation in the group G. So this could be just to introduce some notation. This can be identified with the transporter in the group from P to Q, being the elements of the group G that conjugates P into Q, right? And then we have to divide by the elements that would induce the trivial map, so the centralizer in G of P, right? So for an element Q, I will write the conjugation map in this way. Right. So I like to write the arrows the other way around, like taking the opposite category in some sense. The reason is that when I have a composition of conjugations, like this, x1, x2, and xn, then they define an element, a simplex, in the bar construction of the group. I will write this way. Well, you know this construction, and the way you use it, you multiply the elements when you take differentials, is the way you compose these maps here. So everything goes nicely. Okay. So with this notation, the Martino-Pridi conjecture says that to be complete classifying spaces of finite groups are homotopy equivalent and only if the respective fusion systems where a single suburb of G is isomorphic to the fusion system of H over one of its zero suburbs. So these are isomorphic as categories, or if you wish, we have an isomorphism between the zero P suburbs that preserves the fusion. That's what we write. Well, then we go to the definition of, to extend this concept of fusion systems.
Excuse me, do you have an example of distinct groups that, where these two things are isomorphic?
Distinct groups where these are isomorphic?
Yeah.
Oh yeah, there are many.
There are many.
Well, I don't have some in mind right now, but
Can you just take the group and then take the
probably
the
with,
group
with a pre-prime group, and that's the obvious example. Yes, I think one of the examples in Martino Pridi work is something like, I don't remember exactly, something like SL23, I think SL2 over F3, which has the same fusion system as M11, the Matthew group M11. I might be confused with these numbers, but it's more or less this. And there is no way to write a homomorphism, not even a zigzag of homomorphisms between them inducing this isomorphism. But these are isomorphic, and therefore the fusion, the classifying spaces are homotopy. Yeah, so it was Luis Puig that defines the abstract fusion systems. And at that time, working with abstract fusion systems was considered like a way to reach to this to the proof of this conjecture. Right? So an abstract fusion system is, roughly speaking, a fusion system, something like that, where there is no ambient group, essentially. So we only have the silo and the fusion relations inside the silo. Right? So this means F is a fusion system over finite P group S. Well, if is a category with objects with subgroups of S and morphisms, well, there should be some sets of morphisms, and what we ask is that the conjugations by elements in S are always morphisms in the system, and all morphisms in the system are injections. I mean, group monomorphisms. Right? Furthermore, every morphism can be written as an inclusion composed with an isomorphism. I mean, an isomorphism followed by an inclusion, meaning an isomorphism in the system. Again. Well, there is little you can do with this. And then which introduces a set of axioms, actually two axioms. So let's say the fusion system is saturated if it satisfies two extra actions. That are somehow based on zero theorems, but I will skip to write them down because these are technical and we are not going to use So now saturated fusion systems. So now we have saturated fusion systems are our objects of interest now. So it turns out that the fusion system of a finite group is saturated. Saturated. But it is also true that there are exotic saturated fusion systems, meaning that they don't appear as the fusion system of a finite group, right? And the prime 2 equals 2. We have the say the Solomon Benson example. That's a family of exotic saturated fusion systems at the prime 2, and is the only known so far. So this is a fusion system. Ron Solomon constructed this fusion system that we are now call Sol Q, which is defined over the Silo subgroup Silo 2 subgroup of the group spin 7Q. Q is odd prime power. And he was working on the classification of finite simple groups, so he tried to construct a finite group having this same Silo subgroup, but with a unique class of involutions, unique conjugacy class of involutions, while in spin 7Q you have more than one, 2 or 3. So he constructed the structure of the prime 2, but then he showed that this group cannot exist because contradictions that he got at different primes. And then it was Benson that observed that you don't have a finite group, but there was a space. P-complete space to complete realizing this same fusion system that Solomon constructed. So that's our first example of classifying a space of a non-existing group. Okay, now there is a whole program by Michael Aschbacher to classify simple fusion systems equals 2, and the conjecture is that this is the only family that which is exotic, right? Well, his idea is to maybe use this classification once it's proven, in order to maybe simplify some parts of the classification of finite simple groups. But that's ongoing one project.
Is it easy to say what a simple fusion system is?
Well, yeah, you have to define, and it's possible to define the concept of normal fusion system, and then it's the usual concept.
What is pi 1 and v sol q?
Pardon?
What is pi 1 and v sol q?
Trivial, actually, in this case. Well, this is constructed out of the exotic two local finite loop space of Bayer and Wilkerson by taking invariance by Adams operations. Okay, so that was the motivation to find a way to attach classifying spaces to fusion systems, right? And this is what I want to talk next. So there was a first attempt by Larry Oliver and myself, where we construct sort of extension of a saturated fusion system, which we call a linking system, centric linking system. So it was something like an extension, the category extending this one. Actually, not the category of the whole category of fusion system, but only a full subcategory of the so-called centric objects. This could be, say, C, would be the centric objects. C would be the maximal class. Maximal class of subgroups of S closed by F conjugation Conjugation means just apply an isomorphism from the system. So I say that is F conjugate to Q if there exists an isomorphism in F. So it's a maximal class of subgroups of S closed under conjugation such that the centralization S of P is smaller than P for P in the class. So this means the centralization is exactly the center of P. Right. And then the classifying space was constructed just by taking the nerve of this category. So very easy. And then decondition. And this was, say, the classifying space for F. But there was an abstraction theory, an unsolved abstraction theory to show the existence and uniqueness of this linking system. So the problem was there. And this was solved by, first by Sherman. And Sherman, a group theorist, in, I think it's about, was published 2013. And then he used a constructive way to go from the fusion system to the linking system, and then using the same argument essentially, but translating to the abstraction theory in both. Oliver rewrote this proof at the same time. In both cases, this depends on the classification of finite simple groups. And then it was later that finally Glauberman and Glynn that just remove the dependence on classification of finite simple groups, so free of simple groups. So at this point,
So this is a proof that L exists and is unique.
L exists and is unique. So essentially, what I'm saying is that for a satellite diffusion system, we can attach a unique classifying space. So that's well. Okay, so, but essentially, Andy Cherma was not talking about linking system, but used a different concept, which is partial groups and localities. Well, his idea, he was saying, well, linking systems are categories, and group theorists do not like categories, so we should use some concept which is more appealing to group theorists, so like partial groups and localities. Then, so I'm going to tell you what is a partial group, but I'm going to modify his definition so it is more appealing to algebraic topology. So for me, a partial group will be a simplicial set. Right? So this is a simplicial set. Simplicial set, call it L, such that, put some conditions for understanding. So first, there is only one vertex. Right? So it contains only one vertex, call it B, whatever. And second, more important, we have an operator, Ln, so that's the n simplices, to the product of n copies of L1, the one simplices. Right, so this is n copies. That I call, I don't know if there is a better name, the spine operator, sending a simplex with vertices, say, numbered from 0 to n, to the edges that are numbered 0, 1, 1, 2, up to n minus 1, comma n, right? So for a 3 simplex, for instance, 0, 1, 2, 3, so the spine would be this edge, and this one, and this one. So these 3. Well, so we asked that this is injective. Now, okay, let me add some notation here. Using this condition, we can just write a simplex sigma like x1, xn, and this is familiar if you compare with what we wrote for finite groups. If the spine of sigma is x1, xn, right? And then there is a third condition, is that we want to add inverses. Well, the usual. Why is this a partial group? Well, it's a partial group in the sense of Cherbak. That's totally equivalent, where the underlying set of the partial group is L1. That is the one simplices. So the underlying set is L1. And the multiplication is defined as follows. If we have some elements in L1, then we take the product, say, right. And it's equal to, again, an operator applied to this simplex. If the simplex exists. This exists. Otherwise, we cannot multiply them. That's it. This is why it's a partial loop, because multiplication is not always defined. So pi is an operator again from Ln to L1 that sends the simplex with vertices number from 0 to n to the back edge, means the edge number 0n. So for instance, if n is 2, we could have two simplices, x and y, and then we can multiply them if we have this simplex. Well, this condition says that if we have one, there is only one. So the equation will be well defined. And then this means that this is x times y. That's it. And then the associativity, etc., follow from the properties of the simplicial operators. Okay. Well, I was quite happy with this definition until I found that they are, well, almost never can complexes. So we are limited. We are limited to I mean, combinatorial arguments and these kind of things. It's rather difficult to use homotopy theory there. And they are can complexes when they are real groups. Exactly. But anyway, this allows us to well, to introduce certain language from group theory. We can talk about subgroups. For instance, we say that group G is inside my partial group L. This is a simplicial set. This is just a group. So this means that the bar construction on G is a subsimplicial set in L, essentially. We can talk subgroups. What else I wanted to say? Conjugation, very important. Conjugation, given PQ in subgroups of L and X an element in L1, we'll write the conjugation map like this, as in the group theory, case, sending y to x. But we have to be careful and check that this exists. So this means that this is defined if the simplices are in L3 in this case, for all one. In this case, this is the final conjugation maps. Right, and then we have extensions. Partial groups, and this is easy to define. It's just fiber bundles. So we can use now the theory of fiber bundles of simplicial sets and have extensions of this sort that are the ones of interest to us, where this is a finite group, and this is the finite group, and this will be essentially classified in the same way as the extensions of finite groups, like H3, obstruction in H3 for existence, H2 classifying, etc. And also sections are non-abelian H1.
So by fiber bundle, you mean like twisted complexes?
Twisted Cartesian products, yes. So even when we have a trivial action, when we have a real action of G on L, not only up to equivalence, we can take this twisting function, the obvious twisting function, and have a semi-negative product. There are that I write this way, but we can use the usual notation of semi-negative products in this situation. Right. Well, in this case, we cannot go too farther with this simple structure, and then what Andy Chernak did is to introduce some axioms and define the so-called localities. So, so let's say L is partial group. Oh, I would like to add that my partial groups are finite in the sense that L1 is finite. So this simplifies things. It's not necessary in what I said before, but so when I take a subgroup in L, will be a finite subgroup in particular. So this is a finite subgroup. So we introduce now the prime P, so we are working locally, and so that talk about localities. So we say that L is a locality if there is a family delta of subgroups of S such that we have the following conditions satisfied. So something like x1, x2, xn will be the simplest in L and only if there are composable conjugation maps where each EI is in the family delta. Second, this is on the one hand a restriction on the sort of synthesis we have. On the other hand, this tells us that this can be multiplied, these elements can be multiplied. And you get that the composition of conjugations is conjugation by the product, as you expect. Second, delta is closed under overgroups and conjugation. That means that if P is in delta and Q is a bigger subgroup, still inside S, then Q is in delta. And secondly, if also this is overgroups, and then conjugation means that if P is in delta and we take a conjugation, say Q P, and this is a conjugation, an isomorphism given by conjugation, so I would write this also as U conjugating E, then UP plus Q is also in delta. Oh, sorry, the condition is missing here. If the conjugate is still in S, then it's in delta. We don't want to go out of S. So that's this condition, and the third condition is that S is maximal in the closure of p subgroups, finite p subgroups. Of L. So that's the notion of locality. And now we are able to define, to attach a fusion system to a locality in this situation. So now we can define the fusion system. Locality MS. Sometimes we write a locality as a triple. We want to emphasize the family delta with which we define the locality. So let me do like that. Right. First, you could define something like, as we did for groups, the transporter from P to Q, meaning the elements in L such that there is a conjugation from P to Q. Right. So this exists, it's well defined. And if P equals Q, then we have, this is just a set, of course. NLP, the normalizer, right? And this is restricted now to elements in the family delta. Now this is the same, such that this conjugates P to P. And inside this we have also the centralizer, which is now again u in say NLP, such that conjugation is the identity map. Okay. So what happens is that these are subgroups now. Which is not usually true when groups are not in delta. Right? Now, fusion system of the locality L over S is again a category. It's defined essentially like in finite group theory. So we take objects with subgroups in S, and morphisms are generated by morphisms among elements in delta. By morphisms from P to Q in delta, which are defined as in the case of groups, NL Q divided by the action of the centralizer in L of P. So it's essentially the same definition as in group theory when P and Q are in the family delta, and then for this I mean that you take then all possible compositions of restrictions of such morphisms in the and then you complete the fusion system. Okay, so with an extra condition on the locality, we'll see that this is always a saturated fusion system. Delta contains all the centric subgroups that are defined as in the case of groups. Then calculated fusion system. So the theorem of Chermak actually says that if F is a saturated fusion system, then there exists unique locality yes, with satisfying two extra conditions. Delta equals the family of centric subgroups, exactly. And for all P in delta, the centralizer in L of P is the center of P, and I'm taking now the centralizer in L, not in S. Well, so to a saturated diffusion system, we attach a unique locality, then, and satisfies that the fusion system of this locality is our original fusion system, and then we define the classifying space as simply the key-completion of this locality. So the classifying space is clear, it's just the same, essentially the same simplicial set, but with a decompletion to make things be local. Actually, any locality with same fusion system satisfies that if delta contain all the centers. Only with this condition, just any locality, not only that one, gives us the right p-local homotopy time. Okay. Let me finish this with all running out of time. For example, when G is a finite group, here's the silo, and take delta, say, centric subgroups, or any other family containing centric subgroups, then we define locality S as in synthesis G1 Gn such that, well, that's a condition. It's a string of conjugation maps where each pi is a centric subgroup in this case. So then this is a locality. And then it happens that the fusion system of the locality is the same as the fusion system of the group G, and furthermore, the classifying space of this fusion system defined that way, which is just the decompletion of this simplicial set, turns out to be homotopy equivalent to BGP complete. So we recover the classical classifying spaces in terms of finite groups. But now we know that every separated fusion system is the fusion system of Avogadro. So we have models for classifying spaces. Well, in the remaining time, I'd like to say a few words of what is in the proof of the theorem, of the formula I wrote before. So, so first, we started with a finite P group, I, acting on the classifying space of a saturated fusion system, and this means just any space which is P equivalent, is P completed and equivalent to the classifying space, of the fusion system, right? Then we can form. We want to compute homotopy fixed points, and for this we take first the model construction, so the homotopy quotient, which is now a fibration or fiber bundle like this. And then we use some techniques from former work with Levi, Oliver, and myself, and these new structures to construct a map from the say L, the locality. So created to F by Sherman. I mean, it should be the one that satisfies that extra conditions. And then there will be a map here and an extension of partial groups, such that the P completion of this extension is exactly this bundle. Right? So if this is non-empty, then we've got a section here, which can be translated into a section here, and this becomes a semi-negative product. So call this tau, have a section sigma, and this section produces an action, a honest action. Oops, I need to write it here. That's L. A honest action of pi on L, and it can be arranged in such a way that it fixes the zero. I mean, it leaves the zero stable. So this produces an action so these are elements such as these are usually called isotypical equivalences in this setting, right? Okay, so this action allows now the definition of something like the H1. So we can classify sections by H1 of pi with coefficients in L. I wrote F instead of L before, but the right thing to write here, to put here is L actually. And this is defined as derivations of pi in S modulo some equivalence relation that involves the elements of S, of L, sorry, of L. So that's important. Of course, this classifies the section, so this means this classifies the connected components here. And then for a given connected component, we've got an action. And then we want to define this fixed fusion system. Right? And this is to get to this definition is one of the main questions open in this subject. So to know what is this fixed. At the beginning, I thought we could start with an action of pi on the fusion system, but this is not fine because it could have different liftings to actions in the locality. Right? So it's not hard to see that, for instance, an action on a finite group, which is non-trivial and restricts trivially to the zero. So it's not clear what an action in the fusion system should be. So we talk about the fixed points in the fusion system, but the action is actually defined at the level of the locality. So this is going to be a fusion system with objects in the subgroups inside this fusion system over the fixed points in the zero, and morphisms are such that this can be written as a composition of conjugations where Ci is in L1, is a composition of conjugations restricted to P, of course. But the condition that this homomorphism belongs to the fixed fusion system is that these ones define an inner derivation, and this must be the trivial derivation actually. So the inner derivation defined is as follows. This is equal applied to an element G, so that's a derivation e to s, and this is equal to C1 Cn G Cn inverse, and then continue to G C1 inverse. Well, it's the same relation in group theory, except that we have to iterate and the construction because sometimes you cannot multiply these elements, although this might be defined because there are some parentheses here. Right? So if this inner derivation is defined and trivial, then this defines an element in the fusion system. So with a suitable choice of rho, meaning is fully centralized as I wrote at the beginning. And that's a technical condition. Turns out that is a saturated fusion system over this rho. Right. So we have already the fixed fusion systems. We have the fixed fusion systems, we can construct models that I won't find, but anyway. This is a concrete model, but I'm not going to, I don't have time to explain it. Locality for rho, and once you have this constructed, then you finish like this. So this is Homotopy equivalent to L so that's an index of the indexing for the suitable actions that we take, and this is that's the theory we want to show. That's a very quick sketch, but That's it. I thank you for your attention.
Questions?
So did Shana know about Siegel's work, or did he just reinvent this?
Invent.
Sort of the opposite of Siegel.
Yeah, that's sort of Siegel condition.
It's a
right?
half of Siegel condition.
Half, yeah.
Siegel would ask for equivalence, right?
Well, it depends what they are, simplification sets or simplification spaces.
Uh-huh. So I think for the Siegel condition is that such a map was an equivalence, right? So that's what happens with classifying spaces of groups. So we relax this to be just injective.
Anyone else? If not, let's thank Carlos again and John for all these statistics.